Modern cities are built on a hidden countdown. Deep inside almost every concrete structure we build today, a slow, inevitable reaction is taking place. When a microscopic drop of water enters a hairline crack, it migrates down until it finds the steel rebar holding everything together. This initiates what engineers call concrete cancer. The intruding water causes the internal steel to rust. As the steel oxidizes, it physically expands, exerting massive outward pressure. Within a few decades, it literally shatters the concrete from the inside out. To constantly repair and replace this failing infrastructure, we produce billions of tons of standard Portland cement every year. Producing this volume of material requires a massive, energy-intensive industrial footprint. The core ingredient of standard cement is clinker. Creating it requires baking limestone and other minerals at extremely high temperatures. This intense, fossil fuel-driven thermodynamic process drives off carbon dioxide directly from the stone. Today, cement production accounts for roughly 8% of all global CO2 emissions. We are caught in a destructive loop. We pump massive amounts of carbon into the atmosphere to manufacture a building material that chemically is guaranteed to self-destruct within a single human lifetime. 2,000 years ago, the Romans built the Pantheon. It sits in a seismically active region and has endured 2 millennia of weathering, gravity, and daily use. Yet it stands perfectly intact, without a single piece of steel reinforcement holding it together. At 43.3 meters across, it remains the largest unreinforced concrete dome on Earth. This durability isn't limited to protected buildings. Along the coast of Italy, ancient Roman marine seawalls have been taking direct, violent impacts from the ocean tide day after day for 2,000 years, and they are still standing. The Romans utilized a chemical recipe that was effectively lost for centuries, leaving modern researchers to reverse engineer the material directly from the surviving ruins. The survival of the Pantheon begins with how it manages its own immense weight. The Roman engineers utilized a highly specific material gradient. Down at the thick base walls, the concrete is packed with travertine, a dense, heavy rock that provides massive compressive strength right where the structure needs to support the most load. But as the dome rises, dead load becomes a severe liability. So the builders systematically changed the recipe. They swapped out the heavy travertine for highly porous pumice, drastically reducing the weight of the upper sections. At the top, they left an 8.9-meter hole, the oculus. Removing material at the apex eliminated the need for a heavy, vulnerable keystone entirely. Any rain that falls through is handled by a subtly sloped floor that channels water into a drainage system. This geometric precision ensured the dome wouldn't collapse under its own weight. But physics alone doesn't explain why the material hasn't rotted away. That answer lies deep inside the concrete itself. The Roman architect Vitruvius documented the core ingredients of their concrete: lime mixed with a specific volcanic ash from the Bay of Naples, known as pozzolana. When modern scientists examined microscopic samples of this ancient material, they consistently found small, bright white chunks scattered throughout. For decades, researchers assumed these were simply the result of poor quality control or sloppy mixing by ancient laborers. A recent analysis out of MIT proved the exact opposite. These white chunks are lime clasts. The Romans intentionally created them by mixing quicklime directly into the concrete at extreme temperatures, a highly reactive process known as hot mixing. These lime clasts act as a chemical tripwire. When a tiny crack eventually forms in the structure, water seeps in. But instead of rusting steel, the water hits the high surface area lime clasts, dissolving them into a calcium-saturated solution that floods the fissure. Within weeks, this solution naturally recrystallizes as solid calcium carbonate. It physically glues the crack shut, stopping the damage in its tracks. Modern concrete is passive. It absorbs damage until it fails. The Romans engineered an active, self-healing organism that repairs its own wounds. By reverse engineering this ancient chemistry, material scientists are now working to strip standard concrete of its massive carbon footprint. A company called EMC Volcanics is bypassing the fossil fuel nightmare of clinker production altogether. Instead of baking limestone, they source natural volcanic ash, exactly like the Romans did. To activate this ash, they use a process called high-energy ball milling. Rather than using massive amounts of heat to trigger a chemical change, they use intense kinetic and mechanical impact. The raw material is bombarded with physical force, increasing its thermodynamic reactivity so it can effectively bind into concrete. Because this milling process is entirely electric, it can run on 100% renewable energy. The end result is a highly reactive, Roman-style cementitious material with an incredibly low volume of embodied carbon. We can produce materials that meet modern structural demands without relying on the heavily polluting thermodynamic combustion that drives the standard cement industry. But adjusting the cement recipe only solves half the problem. Modern towers and bridges require extreme tensile strength, which means we still have to use internal steel rebar. To stop that steel from rusting, we have to stop water from ever penetrating the surface. This is where a group called Edencrete is looking to the nanoscale, injecting the liquid concrete mix with engineered carbon nanotubes. Carbon nanotubes are 1/50,000th the width of a human hair, yet possess 30 times the strength of Kevlar. Dispersed into wet concrete, these tubes form an interlocking web, reducing permeability by 50%. This physical shield locks out moisture. By combining these ancient self-healing principles with modern nanotechnology, we can build carbon-efficient infrastructure designed to last for centuries. The path to resilient cities begins with these microscopic reactions.